This is our submission for Formal Lab 1 for Physics 2, determining the charge of a balloon using force of repulsion read as weight on a scale.
Our research question was, can charge be determined through measuring the weight of an electrical repulsive force between two equally charged balloons? And how does the electrical repulsive force vary between the two equally charged balloons at various distances? And the goal is sort of the same.
Shown here is our outcome for three different distances that we looked at with three trials occurring for each of the distances. We calculated the repulsive forces of each of the trials, as well as the standard deviation between all of the trials, as well as calculating the charge algebraically for the three trials, again, with the standard deviation shown.
So we did this to get a better understanding of charges and repulsion through a visualization rather than just a bunch of words like coulombs or newtons.
Shown here is our method and sort of our setup for the lab. We took two equal balloons, we charged them at the same time. We put one balloon into a beaker to hold the balloon still, and we put that on top of a scale. We zeroed everything out so the weight of the balloon and beaker are not accounted for in the final scale reading. The other balloon is then held a certain distance above the first balloon, and as repulsion occurs, the scale should produce a weight that is then recorded. We do the three times for each distances, and then we also did that for distances of 50 centimeters and 70 centimeters as well. We calculated uncertainty using tracker, and we calculated charge algebraically using Coulomb's law.
So here are assumptions and variables for this experiment.
Shown here is how the force of repulsion is calculated. The weight of 1 kilogram was found to be 9.8 newtons.
And then this is how the charge is calculated.
Shown here are our system schema and force diagrams.
So for distance 1, here are each of the three trials. The standard deviations of all the repulsive forces were plus or minus 0.004 newtons, and the charges were plus or minus 1.25 times 10 to the negative 8 coulombs.
Shown here were our calculated repulsive forces and charges for a distance of separation of 0.05 meters. The standard deviation of all the repulsive forces was plus or minus 0.0003442 newtons. And the standard deviations of all the charges was plus or minus 1.3544 times 10 to the negative 9th coulomb.
And then for distance 3, it was a distance of 0.07 meters. And the standard deviations of the repulsive forces were plus or minus 0.0003 newtons, and the charges were plus or minus 4.82 times 10 to the negative 9 coulombs.
Shown here are our average charges of the balloons per distance, as well as the average repulsive forces of the balloons per distance. As you can see, there's a much smaller charge on the balloons further away compared to the other two trials, which makes sense as the repulsive force is also much lower. And this is consistent with Coulomb's law, which states that the force between two charges is inversely proportional to the square of the distance between them. Therefore, the closer the charges are to each other, the stronger the electrical force.
So we use tracker to calculate our uncertainty. There are a couple causes of uncertainty listed on the slide, but we chose to pick the error of the hand location moving. And here are the uncertainty values and a graph of one of the trials at 70 centimeters.
Shown here are our averages with the standard deviations for each of the distances for the electrical slash repulsive force, as well as the charge. Our conclusions were that equal charges can be calculated from the electrical force and the distance of separation between the charges. The smaller the distance between two charges, the greater the repulsive force. And there is no way to tell if the balloons are positively or negatively repulsed without an outside object that has a known positive or negative charge. Thank you, and that is our presentation. And just a quick note, in the interest of time, we elected not to read out all of the numbers as they were, but they are present within the slides if you would like to go back and check.